Okay, do you have any questions about what we had done in the first hour? Okay, so if we just go over, we just determined general properties of rho. In the microcanonical ensemble, we said that it should be constant on the allowed region in phase space, allowed surface in phase space, and it should be zero otherwise, so rho just became 1 over omega. Well, this is the step where basically we relate this ensemble theory to what we had done before, just counting this number of microstates. And, okay, this was the result that we had obtained. One of the results, let's say. Now let's look at exactly the same problem from, let's say, different perspectives. So let's say that this is our entropy. This is minus the integral over phase space of rho, logarithm of rho. Now let me ask you this question. I also have a condition that the integral over all phase space of rho should be 1. What is the function rho that will maximize the entropy? How can we determine this? Well, let's see what we can do. Well, if it's a maximum, if rho is if entropy is a maximum, I can imagine entropy as a functional of rho, let's say. So you give me some arbitrary function of rho subject to this condition. Entropy will have a corresponding value. And if I change rho, in general, entropy will change. In an extremum point, a very small variation in rho shouldn't change the entropy. You see, if you just consider functions of a single variable, at this point, a very small variation shouldn't change the value because it's horizontal at that point. The tangent is horizontal. Well, more or less the same idea holds for functionals. If I consider some variation of rho, the corresponding change in the entropy will be minus dv d rho or delta rho times logarithm of rho plus rho times 1 over rho times the variation of rho. And hence delta S will be minus delta rho logarithm of rho plus 1. Remember, delta rho is arbitrary, but I cannot just set the coefficient equal to 0. Because the problem is, although rho is arbitrary, delta rho is arbitrary, it should satisfy this constraint, and hence the integral over all the phase space of delta rho should be 0. I'm just looking at the variation of this constraint if I change rho. It shouldn't change, but that means the variations should satisfy this condition. Well, if I am trying to look for an extremization problem with a constraint, what I use is what's called the Lagrange multipliers. So basically, I maximize S plus lambda, the integral over all phase space of rho minus 1. As if the condition is met, I'm basically adding 0. Well, this will give me this is equal to minus the integral over phase space. This is not phi, this is the volume in phase space of this many-dimensional space of delta rho logarithm of rho plus 1. This is from delta S minus lambda, my Lagrange multiplier. This should be 0. Now, since I introduced the Lagrange multiplier, I can equate the coefficient to 0. So this tells me that logarithm of rho plus 1 minus lambda should be 0, or rho should be e to the power lambda minus 1. What is lambda? Well, lambda is a constant, so this is constant. How do I determine lambda? Well, I determine lambda from my constraint. If I evaluate this, it should be 1. That is what fixes my lambda. Remember, lambda is just a constant. Lambda is nothing but the normalization of this density of states. It is over there for normalizing the integral of rho over all phase space to 1. So you see again that, okay, we are basically starting the treatment of our system from many different perspectives. On one hand, I had this density of states, etc., defined on phase space. I studied its properties. Then I realized that it has to have such a functional form, the logarithm of rho. That was one approach. Then I assumed that in the microcanonical, well, not really assumed, in the microcanonical ensemble, E and N are constant, so logarithm of rho was constant, etc. That's one approach. Another approach is just saying that, okay, this is my entropy expression, whatever the system is. This is my entropy. And the system will always behave in such a way as to maximize the entropy. Then I ask the question, okay, the system will determine what rho is. So I ask the question, what should be rho so that it will maximize the entropy? And at least since I have just a single condition here, that the integral of rho over all phase space should be 1, well, it told me that rho has to be constant. That is the rho that maximizes my entropy. Let me look at exactly the same problem from a different perspective. I have my ensemble. A total of n copies. Now, I don't know what the microstates of these copies are, but let me say that nr is the number of copies in the ensemble that are in the microstate R. R is just a microstate. So in a sense, knowing all these sets in R tells me what my ensemble is. And of course, these NR satisfy this condition. Now I can ask the question, how many ensembles are there which corresponds to these numbers, to the given numbers? In the sense that, for example, I have many copies. The first one might be in the state R1, the second one in R2, the third one R1. This is one ensemble. I will also treat if the first one is in the microstate R1, the second one is in the microstate R1, the third one is in the microstate R2, etc. This is a different ensemble. Although the copies, the microstates are the same, different copies are in different microstates. In that sense, these two are different ensembles. How many ensembles corresponds to NR? To this set of numbers? Well, you see, if I only know the numbers, if I just shuffle the copies, I get different ensembles. The orders will be different. And I can shuffle everything in this many ways. But let's say if I look at the copies in my ensemble that are all in the microstate R1, shuffling them doesn't give me a new ensemble. For example, if I just change these two copies, I don't get a new ensemble. Still, the first copy is in the microstate R1, the third one is in the microstate R1. So just shuffling an R of them, they don't give me new ensembles. Although here I'm considering all possible shufflings. Among these shufflings, an R factorial doesn't give me a new ensemble, so I have to divide it by that. Well, I have many states, many copies in different microstates, so basically I have to divide by the factorial of the product of the factorials corresponding to all microstates that my system can be in. So let me call this weight of this NR. Then I can talk about the probability that if I give you some ensemble, the probability that that ensemble will correspond to these numbers NR. This probability will be weight of NR divided by, well, it should be normalized to 1, just sum over all possible NR integers. This will be the probability of this set NR. Now I will ask the question, what is the most probable value of NR? Yeah, the numerator is just a constant. So I have to find these numbers NR, again, subject to this condition, which maximizes this omega. That is what I will be looking for now. Well, rather than maximizing omega and R, let me maximize logarithm of omega and R, which will be equal to logarithm of n factorial minus sum over all microstates of logarithm of nr factorial. I remember already in my system I have many particles, many degrees of freedom. I'm making enormous amounts of copies of my system. So there will be many copies in my ensemble that will be in each of the microstates. I'm making really a huge amount of copies. So if for some reason there are no copies in a particular microstate, the only way it can be is because it's not an allowed state. But all allowed states, there are a huge number of copies within my ensemble that are in each one of those allowed states. Again, now I'm making the assumption of ergodic hypothesis. I'm not excluding any point in this allowed space, in allowed numbers, allowed microstates, consistent with my condition of energy conservation, let's say. If that is the case, I can use the Stirling's approximation. You see, NRs, they don't need to be huge to be able to use Stirling's approximation. If you check even around, if n is something around 5 or 10, the Stirling approximation gives you an expression that is the uncertainty error you introduce is less than a few %. So
in this side we have a summation, but in the first line we have multiplication. Take the logarithm.
I'm taking the logarithm of the product. It's the sum of the logarithms.
Okay.
So logarithm of...
Okay, yeah. I understand. Yeah.
Now, Stirling approximation, n logarithm of n minus sum over r logarithm of nr logarithm of nr minus nr. There is this minus n and this n, they basically cancel each other because that's my constraint, and r's satisfy this condition. Now I will again use the Lagrange multipliers because I have a constraint. I will consider logarithm of omega n r minus lambda, well, plus minus, it doesn't really matter. I can just change the sign of lambda, sum over r of n r minus n. And then I will look at the variation of this as I change nr. Well, this will be equal to, well, the first term is just a constant, it doesn't change. It doesn't contribute, so what I get is from the second term, variation of nr times logarithm of nr plus 1. That is the variation of this one. And then I have minus lambda. This is from this term over here. Again, this is just constant, its variation is 0. So this should be 0. You see, the way Lagrange multipliers work is that since delta n r should be equal to 0, well, they are not all arbitrary. At least one of them depends on the other variations. Let's say that delta nr0 is equal to minus r not equal to r0 delta nr. Now delta nr0 is fixed, it's not arbitrary. So if I go back over here, I cannot just say that delta nr is arbitrary and so the coefficient should be 0. I cannot say that because there is this r0 element there. But I can choose my lambda. This is a logarithm of nr0 plus 1. Remember, lambda is arbitrary, it's an arbitrary coefficient that I introduced. I can make this choice. So in that summation, r0 doesn't appear. All the other r's appear except an r0. But I already said that, okay, let me choose r0 to be the dependent variable. All the other r's are independent. So all the r's appearing over here in that summation, when I choose this one, well, they are already independent and hence the coefficient has to be 0 for that equality to hold.
You can have more than one. More than one, R0, R1.
Well, you see, if I have two conditions, not just one, well, it tells me that at least two of the variables should depend on the other ones, so that my condition should be satisfied all the time. So that's why we introduced two Lagrange multipliers, so that in this variation, we get rid of those two dependent variables. All the other variations are independent. So that's the basic idea of the Lagrange multipliers. Well, what does this tell me? This tells me that an r is equal to constant. Lambda is a constant. Now you see, this condition is for r not equal to r0, because r is equal to r0 term doesn't appear above. But this also tells me that logarithm of nr0 plus 1 minus lambda is also 0. So although I obtain this one for the other r's, well, this condition already makes sure that this is satisfied for r is equal to r0 also. So what did we obtain? nr is constant, so all the microstates appear equal amount of time in my microstate, in my ensemble. If I pick a random one in my ensemble, the probability that it will be in the rth state will be an r over r, and again, this is just constant. Since summation over r pr should be equal to 1, but sum over r pr is actually PR times sum over all the microstates of 1. Because PR is constant, I can take it out of the summation sign. But that sum is nothing but omega, the number of microstates, which tells me that the probability that a copy that I pick randomly will be in the rth microstate will be 1 over omega. Remember, when we are talking about averages, well, this is the same thing as ensemble average, which tells me that whatever you put over there, this should be equal to 1 over n sum over all microstates. No, sorry, not sum over microstates, sum over the ensemble copies in the ensemble. But whatever I'm evaluating it, I'm averaging over, it will depend on the microstate of my system. So this I can also write as sum over all microstates. Whatever this value has for that corresponding microstate times the number of microstates I have. Well, this is that's it. Etc. So now we are basically deriving the same result over and over and over again. On one hand, we had this density in phase space. Then we maximize the entropy for this microcanonical ensemble. Then we looked at this ensemble copies, multiple ensemble copies, and we asked for the most probable distribution of the microstates in my ensemble. And they all give me the same result. So any questions up to here? You see, some of these approaches will be more easily generalized to other ensembles we will have. For example, now we will start the canonical ensemble. We will see that it will simplify our life significantly. And, well, basically we will be repeating the same thing over and over again. Of course, now we cannot just talk about the number of microstates available to my system. That will not be valid anymore, but the other approaches will still hold here. Now, what we have in this canonical ensemble is we are thinking basically about a system in contact with a reservoir, if you like, and such that it can exchange energy. So energy is no longer fixed. In the microcanonical ensemble, I had the energy fixed, but now I'm looking at a system in which the energy is not fixed. The number is still fixed, but the energy is not fixed. It can exchange energy with the environment. Well, this is a more realistic system. For example, if you just look at this eraser, well, it's not so easy to isolate it. No matter, even if you put it in vacuum, there will be blackbody radiation around, and hence it will be exchange energy with the blackbody radiation. So we cannot really prevent energy exchange with the environment. So let's just allow the energy exchange. And what can we say about such a system? Well, I can still use somewhat the concept of omega, the number of microstates. But for that, I need to have an isolated system. Let's say that this is my system that I'm studying. It's interacting with the environment. But if I consider my system plus the environment, whatever it might contain, now this is isolated. I have my system plus the environment, everything. There's nothing left outside. So this is an isolated system. Now I can talk about the number of microstates corresponding to this whole system. Now this is the question I will ask. Let me call this my system, the rest is the reservoir. Let me call PR as the probability that S will be in the microstate R, of course, has a corresponding definite energy. This is what I would like to calculate. Well, I have omega SR. Let me call, it will be a function of, let me call that E0. Number of microstates of the combined system. My system and the reservoir. I can talk about omega S, again, the number of microstates, this time of my system that I'm looking at, having energy ER. Then I will also talk about omega reservoir of omega R is the number of microstates of my reservoir having this energy. Now, what is PR? Well, the probability is always the number of outcomes that we want divided by the total possible number of outcomes. Well, the total, in this case, the outcome is the microstates. The total number of possible outcomes is omega SR E0, whatever that is. The outcome I want is that my system will be in the microstate R. There's just a single microstate I'm looking at. So among all the outcomes, I'm looking at the outcomes in which my system will be in one microstate, but then still the reservoir can be in all the remaining microstates. But the reservoir, of course, has an energy E0 minus ER. You see, I'm looking at my system only, not the reservoir. I don't care what the microstate of my reservoir is, but I want my system to be in one particular microstate, R. So that's why I have a 1 over here. Now, if I look at my whole system, among all these microstates that the whole system can have, the outcomes I have is 1 times whatever the possible microstates the remaining, the reservoir can be in. This is the probability that my system will be in the microstate R.
I'm sorry, did we say if we have the energy E0?
E0?
Which is the energy of the isolated system combined S and R. Is it fixed?
Now that's isolated system. That's the total energy of my system plus the reservoir. So it has to be fixed. It's isolated because I want to use my concepts from the microcanonical ensemble. So it is fixed. The whole, I mean, if my system exchanges and can exchange energy with anything else, I'm also including it in my system. So all the system, everything that exchanges energy, that's an isolated system. If you like, this is the whole universe. That's an isolated system. Energy is fixed. Of course, the energy of my system only is not fixed because it exchanges energy with the reservoir. Now I can ask the question, what is the most probable R? What is the probability R? How can we calculate? Well, let's see. Again, rather than calculating PR directly, trying to calculate it in some way, let me calculate logarithm of PR. Which will be some constant. Okay, that constant is actually minus the logarithm of SRE0. That's a constant, it doesn't depend on my microstate R, plus logarithm of omega R E0 minus ER. That is some constant plus, well, we know what the logarithm of omega is. That is how we define the entropy. That is the entropy of my reservoir divided by the Boltzmann constant when the reservoir has energy E0 minus ER. Remember, the definition of the reservoir is that it is huge. So the total energy E0 is huge compared to ER. So I can Taylor expand with respect to ER. So this will be some constant plus SRE0 divided by the Boltzmann constant plus derivative of S entropy of the reservoir with respect to energy. Evaluate that energy is equal to E0 times 1 over KB times minus ER plus higher order terms. Well, so this is another constant. Constant prime, if you like. I know what the derivative of the entropy with respect to energy is. We have defined it as the inverse temperature. So PR is actually some normalization times e to power minus ER over KBT. Well, this 1 over KBT will appear quite often. And so we give it a name, beta is 1 over KBT, Boltzmann constant times the temperature. So the probability that my system is in a microstate R will be determined by the energy of that microstate, and it will be its normal as well. It will be proportional to e to power minus beta ER. Well, the probabilities should be normalized to 1. So the normalization should be e to power minus beta ER, summed over all the microstates. That's my probability of a given microstate. Now, what is the average energy of my system? You see, last week somebody had asked me what is the difference between U and E. Well, E is in general used for the energy of a given microstate. U is the average energy. That's the general use, but not always. And we will see in a moment that it doesn't really matter which one you use. Well, what is this? This is equal to, the average is defined as the probability times the value summed over all the possible microstates. Well, the probability is, we just calculated it, minus beta ER divided by sum over R e to power minus beta ER. Now that sum in the denominator is just a constant, so I just moved it out of the summation sign. Well, let me play it a bit. This is 1 over sum over R e to power minus beta ER the summation in the numerator, e to power minus beta ER. Let me take the derivative with respect to beta, because if I take the derivative of the exponent with respect to beta, if ERs are fixed, they will be fixed, they are the microstates. Well, there's an additional minus sign, let me also cancel the minus sign. Well, I didn't change anything. Minus del over del beta, summed over R e to power minus beta ER. But this is nothing but minus the derivative with respect to beta of logarithm of that summation. Because derivative of the logarithm is derivative of the inside divided by whatever is inside the logarithm. Let me also add at constant volume here. And if you like, we can even add n. Where did we use that? We are not changing n and we are not changing v as we are changing beta. This is a question for you. At which step did we use that v is constant? We did. Yeah. I even told you where we did, without mentioning the name volume. Which factors here depend on the volume of my system?
Internal inertia.
ER. It's just imagine, for example, particle in a box. The problem we studied in our last hour, the ideal gas. The energy was proportional to 1 over the size of the cube squared, or 1 over the volume to the 2/3 power. ER depends on the volume of my system. So moving from this step to this step, when I'm taking the derivative with respect to beta, I am assuming that, well, derivative is just, as you change beta, how does the other function change? At that step, I assume that as I'm changing beta, I'm not changing ER. The energy of the Earth microstate is not being changed as I'm changing beta, as I'm changing the temperature. But that energy, ER, depends on the volume and also the number of particles, by the way. So that is basically, in this step, as I go from this line to this line, I'm assuming that V is constant, N is constant. Any questions? Okay, so you see over here, if I want to calculate the internal energy, I don't actually need to know the probability itself. The normalization constant in the probability already tells me what the average energy is. So that is why we usually define, give this a name. This is called the partition function. And even we don't really actually need the partition function itself, we need the logarithm of the partition function. So U is minus derivative of the partition function, the Q potential with respect to beta at constant volume and number of particles. Let's just look at one more thing, and then we can end today. What's the entropy? Well, the entropy we had defined beforehand is the expectation value of these probabilities. Well, the probability was e to power minus beta ER over Z. So entropy is minus logarithm of P will be minus beta ER minus logarithm of Z, or S is equal to beta times U, the average energy is U, plus the logarithm of Z is logarithm, well, let me just write the logarithm of Z, it's just a constant. Minus the logarithm of Z is U minus KTS divided by KT. Sorry, this is S over K. So there's no K over there, U minus TS. Well, do you remember what we called U minus TS? Free energy. Logarithm of Z is just minus beta times F. And remember thermodynamics. If we know F, then we know everything. So if we can somehow calculate this partition function for a given system, then we know everything about our system. Just taking the derivative with respect to temperature will give us the entropy, taking the derivative with respect to volume will give us the pressure, etc. Okay, any questions before we go? Okay, in the next Monday you have this short exam. And next Wednesday we will pick up from here. And we will look at, for example, what is the energy fluctuation? My system is constantly exchanging energy with the environment. So energy will be fluctuating. How much does it fluctuate? This is just the average energy we have. And we will see that the fluctuations are actually negligible for a macroscopic system. And then, well, our toy, the ideal gas, we will see how the computation of the properties of the ideal gas will be for this system. And we will see that, if you remember, in the microcanonical ensemble, we had to deal with all these 6 n-dimensional integrals, etc. It will be a lot easier to study the ideal gas in this canonical ensemble. So see you on Monday.